Alright, last video on this improved model of the fins. Yeah, finally I'm gonna do this. Why not? I think it's a nice addition. Let me do one last change to this equation because I prefer to have n over 4 here. It's easier to, because until now we've only been talking about, 2 times specific span squared and then a correction term. Then kind of this part we didn't talk too much about. And we assumed it was 1 for 4 fins, so I prefer to put it this way, to get that 2 upstairs. And yeah, I think it's better this way. So yeah, last correction. I triple checked or quadruple checked this correction term. It is correct, so we're good. So what I was telling you is that by the way, I rechecked this and it's the same. Yeah, I told you this. The couple of errors I corrected, it slightly changed the first part of 2.2.19, but it's practically the same, and the conclusions are the same. So aspect ratio. Yeah, aspect ratio plays a big role on this correction term. It's basically an aspect ratio correction term. However, if we have really small taper ratios, so this really small taper ratios means that you have fins that are kind of delta E. Kind of this would be a small taper ratio. Taper ratio 0 would be a delta wing. For small taper ratios, you have an extra penalty. That's called a penalty, the taper ratio penalty. When taper ratio is like really small, I don't know, 0.3, 0.2. If not, surprisingly, taper ratio won't affect much to the lift. And well, the sweep angle, the higher sweep you have, a low. It's pretty smooth. It's not as big as the taper penalty when it goes really low, but you do get a penalty if you go above. I mean, it grows with the angle, but from 45 degrees it starts getting like pretty strong, this penalty. Yeah, just for your information, taper ratio in Rexes is like 0.7 or so. The sweep angle on leading edge in Rexes, yeah, I guess it's like something like 45. I guess it's typical. I told you it's a typical angle. So yeah, we'd like to get this as large as possible, as you'll see in the next section, drag section, to reduce drag. But yeah, we have problems with the lift, with the sweep penalty, and the taper ratio. Well, I mean, it's interesting to get it as small as possible, because if you think about it, well, I'll discuss the taper ratio in a moment. What I'm gonna do is a simplification of this. What I'm gonna do here, well, what I've done is I'm for different sweep angles, like kind of typical sweep angles between 30 and 45 degrees. What I did is I plotted out the correction factor pi in function of the aspect ratio. It was something like this. Okay, so it looked like kind of like a power function. So what I did is I found like a function that could fit, like did curve fit here, and I wanted to find like this pi, if I could curve fit it just in function of the aspect ratio, because what I did is I chose taper ratios that were above 0.3. So remember, if we have taper ratios above 0.3, it's not going to affect the lift. And then sweep angles between 30 and 45 degrees, more or less, typical sweep angles. So yeah, it's getting a bit clogged down here. So I'll do this here. Ooh, running out of space. Well, the pi, I figure out that it was something like, again, this is an approximation. This is like for quick calculations to see the effect, more or less, of the aspect ratio. So you have the complete formula here. Okay, this is for like more precise calcs, but it can be found that the correction factor is something like 1.6 times the aspect ratio, power minus 0.5, which is like nice function, right? So yeah, it does something like this. Yeah, just plotted it just real quickly for you. As you can see, this is aspect ratio, and this is the pi correction term. So small aspect ratios, we get a boost. Yeah, and high aspect ratios, well, yeah, it kind of it is below 1. So yeah, it's just a nice way to quickly see that the biggest factor inside here is the aspect ratio. The other ones, if it's in a normal range, which is like taper ratios that basically you don't have delta wings and leading edge angles, typical leading edge angles. Well, it's basically aspect ratio. So why would we want the taper ratio low? Well, think. Lift is going to be basically only function of the specific span and the aspect ratio. Okay. By the way, this is just it's not that simple, but this could be an analysis. So, of course, we're dealing with systems engineering here, so there is just not a perfect solution. But maybe with these comments, you can have, you can get ideas on how to think, and how to attack problems, complex problems that don't have a simple solution, have a lot of trade-offs everywhere. So okay, so taper ratio doesn't appear here, and we can basically move it from 0.3 to 1 if we wanted, and it wouldn't change this too much. So oops, this is the rocket's body. So imagine we have the specific span. Oh, that's a big specific span. Imagine we're limited. The specific span. Well, what is going to limit specific span? Well, in missiles, it's limited by the launcher. Let's see the constraints. Well, if it has to go in the wings of a fighter plane, well, can't be infinite span, and if it has to go like inside these boxes, don't know how to call them, these launches, well, they're limited by constrained by the launcher you know, you get the idea. And but what we're gonna be mostly constrained in the specific span is the well, if you increase the specific span, we're gonna see that you're gonna need way thicker fins because, yeah, if you have like something like this, well, you're gonna have a super big moment, and here you're gonna have to make the fins very very thick to withstand such a large moment. So imagine that. Okay, we've constrained our specific span to here, and then our aspect ratio. Remember that our aspect ratio is just the. We can put it in many ways. I like to put it in this way, which is the span on one side, and then the semi-sum, the average of the two chords. So this would be the tip, the root over 2. So basically, imagine we could do it the following way. Imagine we decide we want to have 45 degrees sweep to minimize drag, and we won't go higher than this. So the next thing would be, well, what do you want to do? Do you want to do like a taper ratio of this would be taper ratio of 1, and for the same aspect ratio we could do something like this. More or less. So these two fins have the same aspect ratio because the semi-sum of the, so these two sum up the same. So the root and the tip of the two, like the orange and the blue fins, will sum the same. Thus, the aspect ratio would be the same. So the only difference between these two would be the taper. This would have a lower taper, and then this would have a higher taper. This would be taper 1. This would be taper 0.3. Well, theoretically, our approximations say that they're gonna lift the same because they have the same aspect ratio and the same semi-span. So yeah, taper ratio doesn't appear. So which one would you prefer? Well, I would definitely prefer the one with lower taper, because the moment this fin is gonna feel is gonna be way lower. Nope, this doesn't work. It's gonna be way lower in the one with a low taper, as you can imagine, right? So the moment it's gonna be low in this case, because it's yeah, I mean it's pretty self-explanatory. It's pretty self-evident, let's say. The moment is higher. So yeah, but still, there are a lot of trade-offs. Again, here you need a longer root to put your fin. So it's not so easy. It's just just an idea. You can think about it. We still have to talk about the thickness the fins must have to withstand these moment loads. So yeah, it's complex stuff, but hopefully you'll have fun designing your fins. So yeah, unless I see something wrong, this is going to be the last part of the improved model of fins. Yeah, it's been a long series by itself.